Hi, everyone. So thank you for coming on Monday early morning in the middle of the summer. I see there's a lot more people on Zoom, so I guess I can kind of speak more on Zoom. But yeah, thank you for those who came in person. Oh, good, yes.
Yeah.
More folks coming. Okay. So this will be Tongzhou's defense, and the way it will work is we'll first have him give a talk for a little less than an hour, and then we'll do public questions from the audience. And then we'll do the closed session with the committee. That might take up to an hour. And then after that, we'll gather back here for a celebration or consolation, depending on how it goes. So I'll ping on Slack or email when exactly that will happen, but probably around 11:30 or so we could gather back here. Yes, hey, okay, so yeah, I'll give a few sentence intro and then Antonio will say a few words. So Tongzhou has been co-advised by myself and Antonio, and it's just been such a pleasure to have him. His thesis is on representation learning for intelligent agents, and I think that this is like the combination of my two current favorite topics, solving problems by finding representations and then finding representations that make agentic intelligence easy. So it's like such a cool combination. I think he's really spearheaded this. This is a really new area. And I think Tongzhou's role in the lab has often been to bring mathematical rigor and depth to our group, something that we don't always have, but I think he's really elevated the depth and quality of our work, and also educated us so much. Like, I think I've learned more from him than he's learned from me by a pretty good margin. So I'll be really sad to have you go. You've taught so much to the lab and all of us. And the work is brilliant. I'm a big fan. I think it's going to go far and will stand the test of time. So I think I'll let Antonio say a few words next.
Okay, well, so it's been great working with Tongzhou. I think that besides all the great work that he's been doing, he's also been involved in a few projects that have been kind of risky. He's not been afraid of kind of diving into them. And one of them, for instance, was never accepted to a conference, like the dataset distillation paper, but it only appeared on arXiv, but it got a lot of citations. It has a lot of impact, and a lot of people have been working on it after that. So he's been not afraid of doing things that were a little bit outside of the traditional line of work that everybody was following. So it's been great working with him. So we'll miss him a lot if he graduates, of course.
Very cool. So let's see if he'll graduate. So yeah, Tongzhou.
All right. Thank you, Phil, and thank you, Antonio, for the nice words. And yeah, so welcome. Thank you for coming to my defense. And the thesis topic is about intelligent agents via representation learning. And so this title has two of the things that I care most about research, which is intelligent agents and representation learning. So first, I like to sort of define how I think about if this is working. All right, I'll just use my mouse. Right. So first, I like to define how I think about intelligent agents. That this will be the definition that I'll use throughout this talk. Intelligent agent is an artificial system, like could be composed of neural networks or different components that I think should be able to interact with the real world to solve general and complex tasks. And throughout my PhD, I've been wondering, like, how should such an intelligent system look like, and how do we get there, right? But there's no question that tremendous progress has been made through the past few years, right? Through the initial deep learning era and now all the days to the large language models from the past few, from just the last year. And we have seen this trend of going from weak models and strong current models. And the hope seems to have been that if we keep developing these models for them to be stronger and stronger, and eventually they will become at least part of the solution to build an intelligent agent. Right. And if this trend holds true, and maybe we can sort of understand what artificial intelligence actually means by studying how models become strong. What is the qualitative difference between weak and strong models, and how do strong models become, why are they strong? So we set out to ask this question: what really is common in all strong machine learning models? I really mean all, in the sense that regardless of modality, it could be vision or text, regardless of objective, it could be your supervised training or unsupervised training, contrastive reconstruction, et cetera, et cetera. It could be different architectures, or it could be different data set that we're trained on. And by the way we are looking at these neural network models is through the lens of representations. And by representations, I mean vector embeddings that could be directly taken from the output of these neural networks or from its internal activations. And I'll denote this mapping from input data to these vector embeddings as F. So graphically, it could look like this. The input is represented by the apple here, and pass-through network represented by F, and maps me to a representation space lives in this like spherical graphical shape, right? And the orange could be mapped to a different point. And the way we try to understand these representations is to consider how F maps represents different similarity or distances between different points. So namely the kernel that it induces. A kernel is a function that takes in two inputs and gives me a scalar number that hopefully represents how similar these two inputs are. So in this case, I will take the embedding of the first element xi and the embedding of the second element xj, and this dot product between them is the similarity between these two elements. So graphically, kernel could be over a finite set of data samples could be thought of as a matrix, right? Here, we'll see that the kernel between the apple and the orange will have a high value, meaning that they are highly similar to each other. And the kernel between the elephant and the orange will have a lower value. And with this, we can take neural network models and apply them on this paired image text data set that compose paired examples of an image and its associated caption in the text form. And we pass the image side to a vision model that takes in images and give me a vector embedding of that image. And we also take the text side and get the text embedding of its text of the text description of these images. And from each of these, we can get the vision kernel and the text model. So here the vision kernel really represents how the vision model thinks about this data set. And the text kernel represents how the text model thinks about this data set. And then we can compare these kernels as sort of a measure of how well these two models agree in how they view in the relationship of these data pairs. And this gives us a way to compare models at different modalities. And we take this measure and apply them on the best open weight text and vision models that we could find. This is around 8 months ago. There are many more that came out, but we've tested on 11 large language models and 17 PIDs. And we sort of were interested in understanding that. Okay, I was trying to click that. Right. maybe it's good to click that. So annoying. Okay, never mind. All right. Okay. Hopefully I won't block in the future. Right. So we're interested in finding that as we go to stronger and stronger language models, do they align more or less with vision? There are multiple hypotheses that could happen, right? We could have hypothesis one that language and vision are essentially two different modalities. Even though they are shared by some information, they're inherently limited by the amount that they share. It could also be that as we become stronger and stronger in language, we're overfitting to it. And stronger language model actually knows less about vision. And it could be like the trend, the correlation between them keeps going on and on forever. So after we tested it out, this is what we have seen over the models that we have tested. This is testing these 11 large language models and test their alignment to DynoV2, which is the strongest vision model that we can find, at least around 3 or 5 months ago. And what's interesting is that as the models become better and better at modeling language, they also align better with the vision model. And we also tested on the different scales of the Dyno model. Here, as the scale goes up and up, the vision model also goes stronger and stronger. So the other direction also holds as the vision models become stronger, they're also aligning better with the language model. So from this, we seem to be able to say that strong models really converge in representation. And at least over the models that we tested, the best models I have seen so far. We don't really know what happens in the future. It could be that the correlation keeps going on, and this will hold until they fully converge. It could be that it tapers off, or eventually maybe it collapses. I hope not, but that's a possibility. But the point is that at least over the in the stage that we're in, over the model development stage that we are in, as the models become stronger and stronger right now, we seem to be still following this trend. And the same thing holds over a bunch of vision models. And I won't get into the detail of it, but we really want to think about how could they be converged to each other? Why do vision and language models think about the world in the same way? So one could say that maybe it's because they're all transformers. Large language models, vision models, these are transformers. They have the same inductive bias. So we made another experiment where we took 78 vision models with different objectives, architecture, data, et cetera, and measured the performance of each of these vision models by the VTAP task. So here on the left is a scatter plot where each point represents on the right, sorry, where each point represents a model and the color of it represents how strong its representations is at self-diverse downstream tasks. And the distance between 2 points measures how similar two models are to each other. And we'll see that the strong models, the blue ones, are actually very similar in how they represent the images, no matter how they are trained. And this represents a sort of Anna Karenina scenario where Tolstoy may say that all strong models are like each weak model is weak in its own way. So how could this happen? Like, why are all the strong models the same, no matter how we train it? It does not seem to be related to data, architecture, or objective. So here's our hypothesis about why this is true. Right? Even though all those things are different, one thing that holds the same is that all these data and all these objectives are really, the data comes from the real world, the reality that we all share. And the objectives is always trying to model the structure of that reality. And together with Jacob Hug, Brian Chen, and Felipe Sola, in this position paper at ICML 2024, we put out this hypothesis that there is one ultimate representation that as model gets stronger and stronger, they will converge to. And these representations capture the statistical relationship of the underlying reality and is necessary for us to build strong and capable generally intelligent agents. So from this view, like we can sort of consider how to build these AI agents as a representation learning problem. And that's the theme of this talk. So how can we build intelligent agents via representation learning? So let's think about this representation learning problem. If we want to seek a representation of the underlying reality, right, it must be able to solve the vision problems. It can solve classification, segmentation, et cetera, because it has all the information it needs. It also must be able to solve the text problems. It can translate, it can summarize, and similar for other modalities too. And we sort of know how to do these things. Like we can do contrastive learning, mask autoencoder to learn a vision embedding. We also know large language models learn a good text embedding. But what's really missing, so all these can be done through large-scale pre-training, but what's really missing and a lot of challenge of the current era is that how do these models can solve control and reasoning? It's really unclear that what does it mean for representation to solve control and how can we learn such a representation? And that has been the recurring theme of my PhD. And to first try to address this problem, this is what I'm going to talk about, this quasimetric reinforcement learning work consists of a sequence of 3 papers. And we're really trying to push the limit of representation learning for decision making. It turns out that if you get the geometry of the latent space correct, it has a lot of benefits, and as we'll see later. So specifically, the question we're trying to answer is a goal-reaching reinforcement learning task. So the problem goes like this. Your agent interacting with the world and located in a starting state here, the agent may be holding a glass. And eventually you want to execute a sequence of actions and go to the stage where you're drinking water. So the question, the specific question we seek out to answer is that what is the sequence of states? Right? Can we come up with this sequence so that the agent can follow this sequence step by step and to go from the starting state toward the goal state? And we'll call this sequence of states a goal-reaching plan. And to see how representation learning can help us solve it, right? The one possibility is that if we are able to map these states into a representation space, and the representation space captures the dynamics well enough, then we might be able to just draw a straight line in the representation space that naturally decodes to a optimal goal-reaching plan that helps the agent to execute the task in real world. And the way we can sort of think about how to learn such a representation space is through a contrastive-like objective, where we want the representation space to align the neighboring states, the current state and next state to next to each other in the representation space, so that if two states are, if the one state is reachable from the other, they're actually closer in the Z space. And also we want to just push random states apart so that no other states that are not reachable won't be close to each other. And to visualize how this could satisfy what we really want, you can see that if we stretch apart, then eventually any executable path becomes smooth in the representation space. And hopefully that might be sufficient for us to do the geodesic planning that we wanted to in a few slides earlier. So we also know that this essentially is how contrastive loss learns perceptual similarity for image encodings. And the question we're really trying to ask is that, can the similar idea be used to learn a decision-making distance? And actually in the literature, there are multiple papers on this that all tries to learn sort of a decision-centric representation space. But our work is different from them in that we'll show that really picking the correct latent geometry can give us a lot of benefits and improvements over these methods that will show that they're not properly formulating distances are actually less effective. So the exact setup is this. So we're given ways to sample local transition pairs in the following form. We have current state, the action that the agent performed, and the next state the agent ends in, and the cost of that transition. And we'll be able to sample random starting state and a random goal state. These could be in the form of a offline data set or a replay buffer. And then we'll optimize the encoder with this contrastive-like loss. The encoder maps the state space into a representation space where there's a representation space distance labeled as D. The way to read this objective is that we want to subject to the constraint that for every transition that we have seen, the estimated distance between the starting state and the next state are not exceeding the observed cost. And with that satisfied, we just push apart random pairs. And let's see how effective this is. And we'll just start by testing the Euclidean latent distance. And this is most similar to the standard contrastive learning you also see outside decision making. So we tested on this like a simple D4L maze2D task, where you're controlling this little ball colored in green here. And you start from this starting state at this location and navigate yourself eventually towards the red location as your goal state. This is a continuous control task where you're controlling the forces applied to this ball, and the ball has both velocity and the position. If we train the representation contrastive-like objective, this is the representation we obtain, and this is a two-dimensional reduction visualization of it. And as we can see that it actually captures some of the geometry of the environment. You can see that this circle here becomes this donut over here, and then there's this loop becomes this donut. And this is not a really useful view for us to think about the straight line geodesic planning. So in the remaining of this, in the following slides, I'm going to plot the representation in this way, where the y-axis represents the embedding distance from a place toward the goal, and the x-axis represents the embedding distance from the starting state towards that point. And the fact that there seems to be a straight line that connects the start state towards the goal state means that the encoder is able to find the sequence of states from the data set that connects the starting state and next state in sort of like the optimal fashion. And this holds true. So the way we do is that we take all the points along the straight line and extract the nearest neighbor within the data set and sort of try to visualize it. So here I'm going through the straight line and plotting the nearest neighbor. It seems to get mostly the position correct going through this trajectory, but it doesn't seem to get the direction correct, right? As you see, the direction sometimes gets flip-flopped a lot, and there's a sudden jump over there. So there's no way we can make decisions based on this plan because that's not really executable. But what really happened? So it turns out that what we fail to capture is the asymmetrical aspect of these environments. There are so many things in our world that are just not reversible. So if I drop a glass, it's really easy to break it, but it'll take me forever to piece the broken glass back to its original state. So what really means that we shouldn't think about the relationship, the distances between these states in a symmetrical metric way, but really the distance should be asymmetrical. And the Z space, the representation space, is not a metric space, but something we call a quasimetric space. And the quasimetric is just a relaxation of metric where the distance does not have to be symmetrical. And this happens all over decision-making and in our real world, in terms both of natural forces such as gravity as well as time, but there's also like human-defined one-way street. So really, what I'm trying to say is that we should be thinking about representation space where we're not using metric distance, but using these quasimetric distances. And there's a way to formalize this and to parse this theorem. It basically says on the left, we have the set of optimal value functions for a decision-making problem. Right? And this is this function measures the distance between two states and is what we can use to solve control problems. On the right, we say that we're able to show that these value functions has the structure of a quasimetric, and that is essentially what really is the geometry of the state space in the decision-making problem. So how could we model such quasimetric distances? I don't want to get into the full details. There are 2 papers that we wrote on this, but here's the gist of it. So the way we're trying to model this quasimetric distance, there are really 2 requirements we want to satisfy. One is, of course, we want to optimize it through gradient descent, and so that this latent quasimetric function must be differentiable. And second is that when paired with the neural network encoder, it must universally approximate towards any quasimetric or any value function. So it seems hard at first, at least for me, to think about a possible choice. So it turns out it's not that hard to satisfy them. And actually, this is one possible choice. And here, the latent quasimetric is just take the pointwise difference between 2 vectors and clamp them to 0 and take the max of entry-wise max. And this satisfies universal approximation because of triangle inequality. You can manipulate the terms in a way so that it's to see this. And it also can take advantage of the structure within the environment. For example, in this case, where we have a sequence of states, and it takes the cost of 2 to transition towards the right, and it takes a cost of 1 to transition toward the left. And actually, you only need a 2-dimensional embedding to fully encode these decision-making dynamics into a quasimetric space. But of course, there are a few other problems with this. For example, you will see, you can easily see that this can be, the gradient of this is very sparse, and it's not effective optimization. So feel free to talk to me or read these papers that we have a lot of some other ideas to make this more effective. But eventually we're able to have the architecture, have these latent quasimetric functions that are differentiable and easy to optimize. And we take this and plug into this original objective. And theoretically, it is able to stitch together optimal geometry of the decision-making problem from the local data that we observe. So if we run this quasimetric contrastive learning on this same Maze2D data set, and here's what we will obtain. Right? This is a visualization of the quasimetric geometry, where we're plotting over the same axes, the distance toward the goal and distance from the start. And we seem to still have a straight line. And if we do nearest neighbor decoding on this straight line, we not only get the positions of the trajectory correct, we also get the directions correct. And this becomes a feasible plan for the agent to execute and actually follow this sequence of states to eventually reach the goal. And eventually, we do not just want a sequence of states. We also want to be able to choose the action that allows us to follow this plan. So there are a number of ways to extract the policy, for example, advantage-weighted regression and inverse dynamics, for example. We choose to jointly learn a word model that can help us to predict what is the effect of our action. So the way we learn a word model is to take a trajectory in the state space and pass it through the encoder that gives us a latent trajectory. And we learn a latent translation model that tries to model this latent trajectory by taking the current latent vector to perform the action and tries to predict the next latent vector. And we'll learn this throughout with respect to our quasimetric distance. And this objective does not learn via reconstruction or predictability, but really tries to model how actions affect different control costs. And the policy that we learn will be try to emit actions that helps us to directly descend toward the goal direction. And here's a visualization of running a policy to given the current state and goal state, then try to executing the plan. You'll see a smooth trajectory that tries to that go from the starting state toward the goal state. And maybe it makes a little bit mistake, but it eventually goes snaps pretty quickly back to the optimal plan and it goes toward the goal. And we did a bunch of experiments in the paper to really benchmark this over 11 tasks. But I really want to highlight the results we obtained on online reinforcement learning. This is a GCRO benchmark where you're controlling this robot arm to perform different tasks. For example, pushing a block towards a specific location in the environment. As continuous actions, et cetera. And being online, it means that the algorithm needs to both collect data and as well as learn the world, train the policy. And here's the type of plot that we usually see in a reinforcement learning paper. Each plot shows that as the number of interactions with the environment that the algorithm accumulates, how does the performance change? So in the right, we see Quasimetric RL, which is our proposed approach. And what's notable is that it's really, really sample efficient over the next best methods. So across all these tasks that we test about over both state inputs as well as image inputs, it has the best performance and sample efficiency. The underlying technical reason is that it's the only method that among these that directly solves the optimal distance without relying on policy improvement. So in other words, the representation learning itself really doesn't care about the policy. It only tries to learn the underlying geometry of the world. So this is what I like to say what separates from Quasimetric RL with the common usual RL algorithms. It has the exact inductive bias, has a lot of, it has a stable contrastive objective, it is multi-goal, has a lot of benefits. And if there's one takeaway I can bring to you is that decision-making has a geometry. If you're really trying to learn this geometry in the representation space, it is really, it gives you a lot of benefits. And in a sense, it's all you need to do a lot of these things. For example, off-policy action-free learning, you can do planning with these things. And these are decision-centric features that can be trained without the policy, without action. It learns something about the world and doesn't really care that much about the quality of the policy that gathered the data. So with all these benefits, I personally believe that it is suitable for potential large-scale learning and maybe combining with other non-decision-centric objectives. So putting this back into the Platonic picture. So what we really claim is that one way for a representation to self-control is via quasimetric learning by learning a representation of the real world in this quasimetric geometry. And to be able to execute a plan based on this representation is through geodesic planning. But hold on for a second. This is only half a problem. Before we are able to start to solve a control task, we must first identify what the control task is. Right? So towards that, I'm going to talk about Denoised MDP, where we can learn a latent world that is much better than the real world itself. So what do I really mean? Right? So in reinforcement learning, these are the type of environments that we see. We are controlling this robot hand and execute a different task on this arm in simulation. And it's usually very simple and controlled, where you only see the robot arm in a zoomed-in picture. There's nothing else that's going on. But the real world could be different. Your camera may not be perfect. Your lighting may not be perfect. And maybe someone is just watching TV in front of the desk. You also see that within your observation. But across all these three observations, the underlying task is still the same. You're controlling the same robot arm and trying to reach the same green button on the table to press the button so that the lights becomes green. How do we able to tell that they're all the same problem? And actually, this is the easiest one to solve because solving the task of pressing the green button doesn't actually involve watching the TV or something else. So to be able to answer that question, we need to first categorize the different information that we can see from in the noisy real world. So I'll promise I'll return to the robot arm example later, but to be able to categorize information, we need to go, well, I like to use this cartoon example that I always use. So suppose you're just waking up and you want to brighten up the room. And the way you do is that you can open up the curtain and your movement may affect the bird that's flying by and scatter it away. And there's a sun that's shining above the sky, and far away, maybe there is a plane that's flying by. So this simple example actually has different types of information that we can categorize in the world. You have information that are related to your reward. How much of the sunlight you get is depending on how much sun there is outside and whether you open up the curtain. And you can categorize things based on how they're controllable. Your actions affect the curtain, affect the bird, but doesn't affect the sun nor the airplane. But really, what happens is that this bottom left corner, the information that is both controllable and reward relevant is what we care about, right? No matter what the other elements are, the best action is always to open up the curtain. And how can we when we see the real world that has a lot of other noisy distractors, such as the bird and the plane, how do we really identify that this is the core element that I should be focusing on and ignore the rest? And the specific task we're trying to interested is that how can we denoising the observation that we have seen into something that's only contain controllable and reward relevant information so that it has simpler dynamics and easier for us to solve the decision-making problem. But to be able to answer that, let's take a step back and see why traditional methods are not able to solve this. Usually, decision-making formulates the problem in a partially observable MDP, which thinks about word like this. What we see is called observation, represented as O, but underlying true state of the world is what evolves from time steps to time step. So the state variable S gets affected by the agent action, which goes to the next state, and at each time step, it goes through, it emits a reward. And when we model the word this way, it means that every information we see in the observation must be capturing a single state variable, and that evolves. But this is a sort of like unstructured way to represent the world, and we are not really able to directly separate out the different information in here. So one way to solve this is that we can represent the world in a more factorized way. So instead of thinking the state as one single variable, we'll think about it as three elements, where I'll denote it as Z star, Z uncontrollable, and Z reward irrelevant. And the hope is that the Z star will capture the things that are controllable and reward relevant and are the things that we care about. The way we make this distinction is through the seemingly complex dynamics that we impose on this translation structure. There are a lot of arrows, but let me parse this one by one for you. Let's first look at the uncontrollable element. So the dynamics that affects the uncontrollable element is essentially itself from the previous time step. It is not affected by the actions A. It can only additively affect the reward, and hence it's not really, it doesn't really affect our decision-making problem. And the reward irrelevant part, even though it can be affected by every other variable, as long as it doesn't affect the reward or the other variables back, it is fine for us to ignore it as well. And that leaves us with Z star. It must contain everything about reward controllable and reward relevant. And in fact, its dynamics are sufficient to solve optimal decision making because linearity of expectations. And more interesting to me that is that the dynamics of itself also follows the MDP structure, where instead of seeing the full state, we are seeing the denoised state, we have the denoised next state as well as the denoised reward. This really means that if we're able to represent the real world in this way, we can just extract this denoised MDP and use it with our favorite decision-making algorithm. It could be policy training, it could be planning, it could be other different things. So the goal really becomes that how can we learn this full factorized model of the world? So the way we can parameterize this factorized model is also through neural networks, where all the arrows are parameterized by neural networks that mapping different inputs to different outputs. And the problem is really that we're observing these observations, we're observing actions and reward, but we're trying to infer what is happening in the middle. And that actually leaves us with one technical difficulty. And that's, let me explain through this example of the cartoon. Right? So if we learn this factorized word model of this cartoon example, we'll have everything reward irrelevant, potentially captured by by this TO element, where the Z uncontrollable can capture the uncontrollable part. And the hope is that Z star captures everything that we want. But the real problem is that because it has a fully general transition structure, it can actually capture everything else as well. So there's no really guarantee that it only captures this bottom left part that we care about. So there's one extra requirement is that we really want to learn a minimal factorized model where we have the lowest mutual information between the Z star and what we observe. So with that regularizer added on top of the model learning objective, we're able to extract the information that we want. So how can we use this factorized model? So when we want to do decision-making with the denoised MDP, what we have is a raw trajectory that contains noisy observation, noisy reward of the real world, and we'll run through our encoder, and that encoder separates the noise information into 3 different elements, where we have the Z star containing the core important elements, and the others are the ignorable noises. And it gives us a way to transform the original trajectory into the denoised trajectory that can be used for our algorithm, policy, or planner. And you can do, when we run it on the original robot hand example, this is what we are able to extract as the signal, where it's kind of low resolution, but you will see that the robot arm moves. You will see the reward signal, which is the green light, as well as the TV hue change. But all the other noises gets removed into the ignore noise, which are sort of the contents of the TV, as well as the lighting and the camera change. And we'll just pass the clean observation variables into our algorithm, and that will give us better performance, hopefully. And we run this on standard benchmarks, as well as test it on environments where the noises are not really seen in the training. Right? It's able to generalize and become more robust pretty well. And when we test it on decision-making, it has the best decision-making performance of all the representation learning methods that we have tested. So putting this back into the picture, it really means that Quasimetric RL allows us to solve a control problem. And these state abstraction methods allow us to identify the control problem that we want to solve. And throughout my PhD, I also worked on other arrows on this in this picture. For example, contrastive learning, which is really what got me started into representation learning. I don't have time to talk all about that and all the other works, but I'm happy to chat offline. But finally, I want to talk a little bit of what is really I'm interested in the future. So I'm really interested that how can we eventually build a representation that help us move towards intelligent agents. And I personally believe that pre-trained models on large-scale data can help us a long way. It's probably not the full solution, but it will be playing a big role in the solution. But what we really still don't quite understand is what is missing in the pre-trained models. If we test it on some specialized tasks that are perception tasks, the general purpose models doesn't seem to be doing much worse than the domain fine-tuned specialist models. But if we test it on decision-making, a lot of things are still going wrong. Right? Here is me playing tic-tac-toe with the language model. If I represent the board in 2 different ways, and ask the same model. In one case, it gets right, and in the other case, it gets wrong. So it doesn't seem to understand what's really the structure of the decision-making problem that is set out to solve. So the questions I'm interested are these type of questions. It's like, how much does the vision model understand text phrases such as "I believe in freedom of speech"? Does a large language model know decision-making structures of the problem that it tries to solve? So how can we understand, like, if we take the model that is trained in one particular way and try to extract its representation of knowledge for a different task or domain, how well does it do? And what really is missing? Can we quantify that? So in a similar way, right, I'm also curious about video prediction model and what is really missing for decision-making. We have all these good promises of eventually it may be able to simulate the world and solve everything. But how can we quantify the decision-making task, decision-making goal? And here is me coming up with this simple physics word where I have full control of the physics and I know the ground truth, and trying to learn a video diffusion on this data and see if it can help us controlling this world, perform control in this world. And once we understand what is different, and we also need to adapt the pre-trained models for them to be better. So can a large language model actually discover useful concepts and internalize them to improve itself for decision-making? So for example, we know that it's pretty, language models are pretty bad at tic-tac-toe. So I told them that, well, if you see this pattern, it means that you're already lost, because no matter where the X player plays, the O player can choose one of these locations and win. So I'm trying to teach the language model this concept for it to play better, but how can it internalize this concept and actually use it is what I currently don't have any idea for. And also, like, what will be the adaptation data and objectives that can modify the behavior in the ways that we want? We start from a pretty powerful pre-trained model, but what is the difference, capability difference from it towards a task expert model? And throughout my PhD, there's my other lines of work that focus on what is the sufficient training data that is for training tasks that hopefully maybe can also be similar ideas can be used to analyze these type of questions. And finally, with all these wonderful pre-trained models and new language models coming up every day, how can we combine all of them and actually get the best of best of all the worlds, essentially? So these are the type of questions that currently are very interesting to me, and I'm very excited to think about them and hopefully work on them in the future. So I end up my technical part of my talk with sort of a philosophical question. So as I prepared my talk, my whole talk is motivated through this Platonic representation example. So I said that to really learn a representation of the true reality, we need to do pre-training to learn from existing knowledge. We need to combine different modalities to get all the information. And we maybe need to be a little bit active. We need to interact with the world, get new knowledge, new concept, verify them, and internalize. So I can't help but extrapolate a little bit and think about this is kind of similar to what we do in science, right? I think in the scientific method is that we learn from the textbook, learn from the existing knowledge, and go ahead and experiment and try to build up new knowledge about the real world. So the philosophical question I have is that really is the capabilities that we need to build intelligent agents, is it similar to automating science? If there is a similarity between these two, and if the latter is a good goal for us to pursue, I don't really have good answers, so I'm curious to hear the thoughts from all of you. So finally, I'm going to talk about some of the most important people throughout my PhD. The people who made my PhD possible. So first, I'd like to thank my advisors and thesis committee. So Phil is my advisor, of course. And Phil taught me a lot about doing research, especially in how do we think about research problem, how to present the problem in the best way in terms of writing, and as well as presentation. There are multiple throughout our one-on-one meetings there are conversations about what is really going on in the field, and what will be going on in the future, what happens with intelligence, and what happens with deep learning. And all of these are questions are like really never really thought about before coming into PhD. So I remember before my PhD at Berkeley, and Phil and I sat down like in Alyosha's office. And the first sentence Phil said to me is that I won't be doing vision much. I will shift my focus into understanding intelligence. I didn't understand what that means, but I thought, oh, that sounds cool. It seems related to deep learning. I want to do it, right? So I think like it's really around the third year, I really understand what it means to doing research on artificial intelligence. And actually I shaped a lot of my research views, as you can probably already see through my defense talk. So what I really also appreciate Phil is that Phil gave me a lot of perspectives and helped me to understand the research and understand what our big questions are. And also Phil gives me a lot of freedom in terms of choosing the research directions I want to pursue. And you'll see that you have seen that I worked on reinforcement learning a lot, which is not the expertise of Phil, but he allowed me to not only pursue it, but also doesn't really just like let me off. And he'll sit with me and try to understand what I do, and also brainstorm and doing research with me to help me also become better at a project that I want to solve. So I really appreciate you for essentially teaching me a lot of the research skills as well as shaping my research interest. And also Antonio. So I think about Antonio as the person who always have the coolest and the most crazy ideas. And what's really great about Antonio is that all these crazy ideas will turn out to be very useful and true 3 years later. So the first time I worked with Antonio is in 2017, and Antonio was talking in the intro is on data set distillation. And totally crazy idea at the time. So crazy that I tried to submit it 3 times. Each time I made major improvement, and it didn't get into any of the conferences. But right now it's my second most cited paper, over 550 citations. But over the times, there's like stories of Antonio's crazy ideas where no student wanted to work on, but eventually we realized, oh, that would have been good. So another good example is the learning from noise picture led by Manel and Jonas. So another thing about Antonio is that Antonio always full of energy and enthusiasm, especially in his talks. So many times, like other students reach out to me and ask, like, what topics does Antonio really like? What is his interest are? So I always struggle with that question. I feel like I don't know, he's the most like curiosity-driven type of person that I've seen. And it has like really passionate way of approaching research and life that has affected my view a lot. And I thank you for that. And there's Leslie. So the first time I interact with Leslie is in my first year in the EI seminar, where Leslie was one of the 3 instructors. And the second time I interacted with Leslie was in my 4th year. So there's a 3-year gap between them. And when I approached Leslie, I was kind of, well, it's not like we didn't talk with each other, but we didn't interact that much, right? And when I approached Leslie, I kind of surprised that she still remembers me and knows what I do pretty, well, much better than I expected. And Leslie is always a nice and patient person and listen to what I say, and also very sharp in like thinking about research and answering my questions. And Leslie has taught me a lot of like how to think about the big problems in decision making and what really is fundamentally hard or easy from the current part. And every time I chatted with Leslie, I learned a lot. And I thank you for thinking about research with me and discussing career options. And also thank you for zooming in from Singapore late at night. And that's Stephanie. I don't know if you remember, but the first time I visited MIT during my visit is like a special visit day because I came off schedule. And I reached out to a bunch of people, and you're the one of the few that replied. And at that time, you were not physically in school, but you arranged meetings for me with your students, and I talked with them. I learned so many cool things that are going on with the group, but I also learned it's a very math happy group, and I kind of got scared. And but eventually, like throughout the years, as I come into MIT, I work on these like representation learning problems. I realized that my interest has overlapped with a lot with what you and your students have been working on structured representations, on how neural networks represent and map data into concept into representations. And in the deep learning class as well, and where I serve as TA, and you taught me a lot about how to do teaching and mentoring, and what is the most effective way to teach different concepts to especially students who are just starting. And thank you for that, and thank you for zooming in from Germany. And these are the 4 people that I'm really fortunate to have on my thesis committee. Oh, I forgot to say, like Antonio is also really, really good at figuring out where something is kind of fishy. So this is me a few weeks ago and trying to pretend I already graduated and trying to take picture with them. And obviously, I think Antonio knows something when I did that. And also a larger group of people that I really want to thank for is my collaborators throughout my PhD. There are so many, some of them I had many papers throughout many years. Some of them are short collaborations. And regardless, I learned something from each one of you. And without you, none of my research would be possible. And for that, I'm truly grateful. There are so many more people who helped my research or my career, but are not on this slide. There are just not enough space to fill like over 100 or 200 people. And there are many people who gave me suggestions that improved my research, that affected my career choices. And some people I had stimulating conversations with them, and which led to productive projects. And there are also some people I worked before my PhD and has introduced me to get started on research. And there are some people who are collaborators for ongoing projects. And they always teach me something new every time I talk with them. I'm sincerely thankful to all of you, people who are on this slide. And if you're not on this slide, sorry, there are not enough space. There's also my lab mates, right? I was very fortunate to be in 2 labs. So I mostly show pictures of lab dinners in this slide, but trust me, like throughout the 5 years, we have a lot of wonderful events. So for example, one of my favorite ones on the bottom is in the retreat to Acadia, where we sit down on the firewood and have marshmallows, but I don't think we talk about research, we talk about life, right? Which is like one of the most interesting experiences. Yeah. So every member of the labs adds a little bit of their own identity to the lab. And it's made the labs a colorful, fun, and a very unique space to be in. And one thing about academic labs is that people come and go, and the labs are composed of mostly different people from 5 years ago when I started. But even though the people are different, like to some extent, the labs feel the same. And Antonio, Philip, and Fern have spent a lot of effort to make sure that the labs always have a welcoming atmosphere where everyone can actually achieve what they want. So in the future, I'll probably gradually fade out from the lab, but I'm sure that Antonio and Phil will keep the lab a great space for research and learning. And whenever I return, I think it will be a familiar place. And also my friends. Like over the years, I made some of my best friends of my life throughout the PhD. So when I graduated from undergrad, I moved to New York. And the one thing I realized is it was really, really hard to make friends. And that's even hard to make good friends. So this is a picture where I took with my friends before I left Berkeley and came to New York. And during my time at New York, and I always wished I was closer to them, and they're on the West Coast. And then I came for grad school, and I thought it will be the same. It will be hard to make friends. It will be harder to make good friends. But maybe I'll just spend more time doing research, because at the time I thought like research is fun and grad school is full-time doing research. So wow, that should be pretty low stress, right? Well, but I was wrong. I was wrong about making friends, and I was wrong about research. So grad school is like a roller coaster of emotions. There are like stress, excitement, depression, and happiness. And throughout this roller coaster, I became friends with the most amazing group of people that I have met in my life. So sometimes we talk for hours about research and life late into the night. maybe a little bit of alcohol to stay hydrated. We're on the same emotional roller coaster throughout the grad school, where we helped each other and shared important life moments along the way. So on the bottom right is the day of my wedding, for example. Sorry, I'll take a few minutes longer. So many of my PhD friends and pre-PhD friends are in California, and I look so much forward to moving there and hanging out with them again. Oh, you're not happy? All right, so also my family, right? So nothing really beats seeing the family, but being an international student with exactly 12 hours of time difference from home isn't very easy. I don't get to visit my parents and my brother that much, and both due to visa and the pandemic, essentially. But fortunately, my family made efforts to come visit me as much as they can. So on top left is a picture I took of my parents in 2017, which is the year I graduated from undergrad. And since then, I have only been back 2 times. But the other pictures you have seen here are from them visiting me in California, in Boston, in Hawaii. So I really thank you, Dad and Mom, and my brother Andrew for always being there and supporting me. And it really means a lot. And throughout the years, I've also received great love and support from my cousin's family and my wife's parents. And I've been showing them around Boston. I talk with them frequently, either in person or via video chat. I then realized this until very recently, but their trust and support in me gave me so much energy and strength that sustained me through grad school. And finally, I want to thank Lexi, my wife, who sits right there. And Lexi is the most important person in my life. And together we shared many defining moments of our lives. So for some time before, we lived separately in different countries, and then in different coasts, and then in different cities. And then Lexi moved to Boston in 2020 in support of my PhD. And together we've lived and traveled through many amazing places, like we in Shanghai, in Chengdu, Qingdao, Seattle, San Francisco Bay Area, New York City, Williamsburg, Charlottesville, Washington, DC, and we've been to places like Shenandoah, Acadia, Japan, and there are many more places where I just didn't have space to put on. We spent many hours together doing all sorts of fun activities. We've been to museums together, enjoying nature, especially the ocean. We play badminton, table tennis, and video games. We cook together and go out to restaurants together, and then enjoyed every second of it. And it made the life very meaningful to me and worthwhile and so much more enjoyable. And that's motivated me to do my best in life and work. So I'm forever grateful for your love and support, Lexi, and I'll continue to give you my best support and love. To you and to our cats, Tabby and Mochi. So Tabby and Mochi joined our family at the height of pandemic in 2021. They arrived at our tiny apartment with just 3-month-old. Now at age 3, they're probably 5 times heavier, like 6 times larger, and I'm sure like 20 times louder. So there are many times where I just stay late in the night because I want to enjoy some time without their meals. So I'm pretty sure that they reduced my work efficiency in half or something. But I don't regret it a single bit. They brought so much more love and happiness to us. The way they express their love to me, which is often rubbing their head against me, melts my heart. Their like sort of carefree lifestyle is something that I aspire to every single day. The PhD would be so much harder without them, and I wish their lives to all be always healthy and full of love. And finally, I want to thank all of you, either in person or in Zoom, for coming to my talk. And thank you for listening to me for rambling for 1 hour, and I'm happy to take questions.
Your time for, 2 questions.
Yeah, Adrian.
I want to ask about the Denoised MDP.
Yeah.
Where you factorized that it's sort of the control over and like reward dependent.
Right.
So I wanted to ask, like, when you separate sort of like the thing that controls reward but it's not controllable, that you made the effect on reward additive.
Yeah.
I wanted to ask like how reasonable that assumption is in practice.
Right.
Like imagine a situation where you have like a water current that can flip directions.
Yeah.
Which obviously you cannot control, but it would influence what the optimal decision might be. So I just
Good question. So the question for people on Zoom, the question was about whether in the Denoised MDP project, in the reward irrelevant information allowed it to be additive to, in the uncontrollable information allowed it to be affecting the reward additively. How realistic is that assumption? So the answer to that question is this. The additivity assumption is made it so that I can easily discard it when the objective is expected reward because of linearity of expectation. And there are cases where things are not additive and you really can't ignore it. For example, a traffic light. And so that won't affect your reward additively. Essentially, it's probably 0 or 1, a sort of multiplication kind of thing. And you shouldn't really ignore the traffic light when you are driving. So maybe there are more cases where it's not additive, but you can still ignore it. But maybe it's I didn't really think about it too much in terms of what are the exact conditions. But additivity is for sure that theoretically works and seems to be working pretty okay in practice, because you can easily add two Gaussian distributions together to get another Gaussian distribution that makes implementation easy as well. Yeah. But good question. Like in short, it's there for theoretical reasons. Maybe there are ways to relax, but I don't really have concrete answers for how to relax them. Right.
The quasimetric representation.
Yeah.
So you mentioned that it's meant to a platonic representation. So
Right.
have you found that like pre-trained language models or pre-trained vision models have somewhat easier ways to convert to quasimetric space? Or?
Good question. So the question is that for the quasimetric work, I made connections about between it and the platonic, and if there, does that mean that it will be easier for us to adapt pre-trained representations to be quasimetric? I should really try that, and I hope so, but I don't have answers because I haven't run the experiments. But my hope is it will be useful. Yeah.
I talked about the representation in the multivariate setting.
Yeah.
Because let's say in languages like left and right are very hard to distinguish just from language per se. It was much more easy to distinguish.
Right.
So like fast and slow.
Right.
It's much easier to think about fast and slow in the video setting, but much less so in
Right. Yeah.
like language setting.
Right.
So how do you reconcile to that
Yeah.
representation with where I think just maybe just fundamentally vague?
Yeah. Good question. So question is that there are concepts that are easier to identify in one domain versus the other. For example, left or right are easier to identify in vision, but sometimes harder in language. So I totally agree with that. And so that might actually be, that probably is one of the reasons where you should learn from multiple sources and multiple modalities. There are some relationships that even though you have signals, you have cues from in one modality, it's just much easier to learn from the other. Okay. And so I didn't really list it, but one of the questions I want to investigate in the future is how can we use better cues from another modalities to learn about your modality better? Yeah, so I personally believe that will help, but in what way and how much is something that still need to be explored. Yeah.
Any questions on Zoom?
Yeah, if people are on Zoom, please just shout out. Okay, I guess that's it.
Any last questions? Okay.
If you remember, what's like the x-axis and y-axis scale of the platonic?
Yeah. So I'll just show you the scale. You mean these ones?
Oh, I guess no. Yeah, I guess here the original one.
This ones? Or it's the similar scale with the second plot. Well, and it's kind of hard to understand this scale without understanding the metric a little bit better. That metric essentially says that if I take nearest neighbor in one modality and nearest neighbor in another modality, how much do the set agree with each other? So the best value is 1, and the smallest value I think is 0, right? And so it could be arguable whether 0.2 is large or not. yeah. But so that's something like it's really what we really don't understand is what's the remaining 0.8. But that maybe should be about the trend that will happen in the future. That is kind of hard to understand. All right, thank you. Thanks for coming. Yeah.
Time to click on the button.